Let's take another look at the hydrolysis of these triacylglycerols, because when we want to break down one of these molecules, we need to hydrolyze it, right? Hydrolysis is breaking apart via water. We're using water to insert within the bonds that are holding this molecule together in order to split it into the pieces that it is made up of and therefore, gain access to whatever we're trying to do with it. And so here we have our triglyceride. So we have 3 bonds that are shown that are the bonds within the ester that are going to be broken. And for each of these bonds, we will require 1 water. And when we do this, we break the water apart and we're going to make 3 stearic acid fatty acid chains. These are the chains that are on the one side of this triglyceride, and we're going to pop out that glycerol molecule, which looks like this. It's 3 carbons connected to each other with an OH on each of those. This is really that kind of linking mount for these fatty acid chains, which, because we've broken it apart with hydrolysis, is now free to do this reaction with some new fatty acids as needed. When we break those apart, we have this fatty acid, which can be turned into a soap. And so soaps are a really, really important example because it leads us to understand how lipids self-assemble into really, really important structures like our cell membrane and things like that. This may not be as relevant biochemically, but it is a really important example of just like how soap works as far as washing your hands, why that is highly effective, way more effective than water, but also it is really reflective of the self-assemblies that are done by lipids in biochemistry. And so if we prepare one of these fatty acid chains in the following way to get its conjugate base by getting a negatively charged oxygen deprotonating that carboxylic acid, we're going to be left with one of these soap molecules. And so again, we do it like so. This is that same hydrolysis in effect, where if we do this with a lot of base, we're going to end up with deprotonated acids at the end. And so maybe you've even done some soap making, or you understand the process of soap making, where what you begin with is 2 things. You need fat and you need lye. And lye is NaOH. You need fat because this is the source of your soap molecules. And you can do this with any fat you want. You can do this with some kind of an oil, or you could do this with some kind of an animal fat. And traditionally this was made from animal fat, as that was kind of a byproduct of what was available in agriculture, right? The meat is great for consumption, but there's just too much fat on a cow or a pig for anyone to eat all of, and so you can turn the rest of it into soap. And so this is the molecule that we're looking at, right? And when we look at a molecule like this, it's important to note a few really important things about this soap molecule. And the first is that there is this sodium here, but for the most part, let's just ignore this sodium. This sodium, and sodium really in a lot of times where it's paired with a negative ion, is really just there because we don't have pure negatively charged stuff just sitting without any positive stuff nearby. Sodium is for the most part relatively inert, and so when we have this, it's just the leftovers from the sodium hydroxide that's ensuring that this isn't a negatively charged molecule floating around with no balance to it. In short, you can ignore it. It's not going to participate in this reaction, but it's necessary to demonstrate that it's here because we can't just have this soap molecule all by itself with no positive counterbalance. Let's think of a couple of questions here. So here we have what's left over from the carboxylic acid, the carboxylate side. Is this side polar or nonpolar? And if we look at the hydrocarbon side, is the hydrocarbon side polar or nonpolar? Go ahead and pause here for a second and determine what you think about each of these 2 sides of this soap molecule. All right, so hopefully you've thought about this a little bit. The carboxylate side is polar, while the hydrocarbon side is nonpolar. And so this is the origin about why this soap molecule does its soapy thing, right? Because what is this going to mean for its behavior in water? Well, it means the following, that when we put a bunch of these together, right, we form what's called a micelle. And this is the overall picture. We'll look at this again in a second. But remember here that the nonpolar hydrocarbon side, these want to find each other, and they also want to find any other nonpolar stuff that might be around. Whereas the carboxylate side, this is polar. It wants to find the water. And so what happens when they're allowed to do these things, right? The yellow side wants to find other yellows, and it wants to find any sort of nonpolar stuff that's also around, whereas the carboxylate side wants to find water and itself. And so it makes this micelle. The nonpolar sides of the soap grab onto any grease or anything that might be sitting on your hands, and it captures it on the inside while they're attracting one another. The hydrophilic heads, they face outside to the water. And we make this little bubble that's called a micelle, where it achieves a nonpolar environment in the middle and a polar environment out on the outside where it's hydrated by the water molecules, or rather interacting with all the water molecules. Now that you have this bubble, which is hydrophilic all the way around, you're able to just wash it away. You capture the greasy stuff and you wash it away in a micelle. This theme is really key to understanding how lipids engage in biochemistry, as we're going to see in just a little bit here, and also describes how soap works. We don't really need to have antibacterial soap or anything in addition to the soap that would kill bacteria, because this micellization process is so effective. You're going to be changing the environment so radically and sweeping everything away that something like antibacterial soap may be adding to a process that already sort of works well enough.